So it should be pretty easy lab today, which is good, because you may be behind on other labs and you want to get those done. Questions on any of that? We've got 3 weeks left, so we only have 6 more times that we meet. It's kind of sad.
Unless there's a power outage.
Right? Huh?
Unless there's a power outage.
There's a power outage. I can't imagine
That would
the fact that it rained for like 4 days straight that we're going to have a power outage. Right? You never know. We could get, 100-degree weather for 2 weeks straight. High winds and something will happen. But yeah, if that happens, we'd be worried about other stuff as well. So we have 5 lectures left and then a final. So that's kind of what we have set up for the rest of the semester. The last assignment is on Canvas. It's a tree lecture. So just like your DL node or your doubly linked list was built off of our 3 or 4 linked list labs, the last assignment is built off of the next 3 labs. So I would read it over at some point, but usually I say, oh, I gave you 3 weeks, you should start on it soon. You can make the tree node pretty easily right now. But until you get today and the next 2 labs, there's really not much that you're going to do on it. Does that make sense? So I make the node for it. You can do that after today, but I want to worry about the other stuff. That's why I gave you the how to do. Good? Questions? We good? There's no one in the back row. I don't know. I scared them all away. So let's talk about trees. I kicked the nickel. I don't know. I still make nickels? No, just joking. Box of cereal is like $10, right?
$10.
You ever like watch like celebrity stuff? How much does a box of cereal cost? I don't know, $15, $20. They don't ever buy their own cereal, right? Probably does cost them $15 or $20 to hire someone to take it and do it.
That's what I charge someone to.
Right, exactly. Someone asked me to buy them a box of, oh yeah, it's like $50, right? So we're gonna talk about all of this stuff. So when we get to trees, we talk about the fact that all of our other data structures have been linear, meaning, right, in an array, index 0, then index what? 1, and then index 2, and then index 3. In a linked list, it's what? First node, then second node, third node, right? And in a linked list, we have links, right? To the next node, to the next node, to the next node. And a double linked list, we have also links to what? Previous node, previous node, previous node. Right, we're good with that? So everything's been linear. Trees are not. So the linear ones kind of have this before and after relationship, right? This is what came before and this is what came after. All right? Trees, right, are different. They're not linear, right? They branch. Hence the name that they're trees, right? They have branches. But they're very fundamental. We use them all over the place because they're very efficient. So they branch, they're hierarchical, okay? Meaning that they have layers. Right? Layer 1, layer 2, layer 3, and layer 4. But the way these layers look are different than a linear, right? First node, second node, third node. But they are made up of nodes, yeah, so nodes still exist, right? And so we're going to go through a couple things, family tree, file system, that kind of stuff. So here's a family tree, right? It has layers, four layers in my picture, right? Because there's the U layer, right? In a family tree, that's you on the bottom, right? And then there's your parents layer. Right, and then your grandparent layer, and your what? Great-grandparent layer, right? So there's trees, but there's relationships, right? Because there's some relationship between you and your parents. There's some relationship between one of your parents and what? Their parents, and some relationship between one of your grandparents and their parents. Everyone see that? So there's still this kind of before and after, but it's organized differently, right? In this case, right, in layers. There's a Linux file system or a Unix file system. Right, everything starts at root. Okay, and if you want to read this, right, here's the root directory. In that root directory, you have 1, 2, 3, 4, 5, 6, 7 more directories. All right, Windows file system works the same way. It's just not root, but right, we have a directory, and inside of that, we have more folders, right, more directories. And inside of each of those directories, like the etc directory, we have what? More directories. Inside of the users directory, we have more directories, right? And this one could also have what? More directories. So file systems can be set up in a tree-like structure because it makes sense for what they do and how they store things. I told you it wasn't too hard, right? Trees don't look too bad, right? As far as conceptually what they do, right? If I told you, okay, can you go program a program that builds a file system? You'd be like, maybe not. That seems a little bit harder, right? But overall, trees aren't too bad. But trees do have a lot of terminology. So we don't really learn a lot of terminology in this class per se, but with trees we're going to learn quite a bit. And you'll be experts by the end. So the top node of a tree is called the root. It's the root node. They're trees, so it makes sense, right? Trees have roots. That's where they start. They grow up from there, right? A lot of times we'll actually put the root on the top there. Trees a lot of times grow down, not up. I know it's crazy. Every other node in your tree has a parent, okay? So the root node, I call it the God node, right? It has no parent, but everything else, right, is going to come from that. So every other node in your tree will have a parent except for the what? The root node, right? Root node has no parent. And every node has 0 or more children, meaning you don't have to have children, right, in a tree. Optionally, nodes have children, but children always have what? Parents. Good. So here's my lovely tree, right? What's the root node? 2 is the root node, good. Right, and you'll notice that every other node has a parent, right? Every other node has one parent. Right? And then these children, right? Or these nodes don't have children, right? 2, 5, 11, 4. We have special names for those. They don't have any children. Right? There we go. Parent of 9, child of 7. Pretty easy, right? Nodes that have the same parent are called siblings. Once again, not profound. If you share the same parent, then you're siblings. All right, we're going to go back. Right? Internal nodes have children, so nodes inside the tree always have children, and then leaves, right? Kind of like fall terminology, leaves, right? Don't have children. Those things on the outside, right? So think about the inside of the tree, right? Right now it's pretty easy because all the leaves have fallen, right? The inside of the tree is just the sticks and branches. Those are internal nodes, and then the leaves are the outside of things, right? Those are the things you really see, right? And so that's what we call them. So 7 is a sibling of 5, right? Just like 6 is a sibling of who? 2. Now, 6 is not a sibling of what? 9. They are on the same layer, right? But they do not share the same parent, right? So they are not siblings. They're cousins, right? We don't have that term. Right? 5 and 9 are internal nodes because they what? Have children, good. And 5, 2, 11, 4 are leaves because they don't have children. Good? All right. We also, I think you're trying to get, we have this idea of ancestors and descendants, right? So the ancestors of 11 are who? Good. Look at that. I have a little animation. Right? They're all ancestors. Right? Descendants of 7 would be? Right? Should be 2 as well. I just didn't have it. Right? So up the tree, right? Our ancestors, down the tree are what? And then this one's key. Okay? A subtree, and we're going to talk about subtrees a lot with the way we're going to write our algorithms. A subtree is a tree inside of a tree. Meaning that you can basically pick any other node in a tree and say it's a root, right? And then it is its own tree. So right now my tree, 2 is the root, I have all these other nodes. Everyone good with that? But if I just look at 7, 7 can be the root of a different tree, a subtree, a tree within a tree, right? Because 7 would be the root, and 2, 6, 5, and 11 would be the what? The children? Does that make sense? So subtrees are trees inside of trees. Anyone know why this is useful for us? Great.
We can divide things up into smaller and smaller pieces to work with.
So we can divide things into smaller pieces to work with and run the same algorithm on those pieces. Because they're trees, right? Subtrees are just trees. Do we have a mechanism where we can run the same thing over and over again on the same thing? What is it? Recursion, right? Go figure. Remember, recursion is good for you because the solution is elegant. So it'll actually end up making your algorithms a lot easier. No loops, right? Assuming you do it correctly. All right, so subtrees, good. Path is how you get from one node to another. right? So from 7 to 5, the path would be through 6, right? We're getting a little bit into graph theory as well. That just sounds cool, so I'm throwing it out there. Graph theory is all about, right, the interconnection of nodes, right? Ours is directed, right? 2 is directed this way. You can have graphs that can go both ways. There's no direction. But we don't have to do that. You guys got to do it in discrete a little bit. Levels, how far you're from the root, right? So basically we're looking at layers, right? Level 1, level 2, level 3, level 4, right? Edges are the connection between nodes, right? These are edges. Hopefully you realize in code, your edges are going to be what?
Pointers.
Pointers, right? 1, because they're arrows, right? And 2, right, that's how we're going to connect a node to another node is via a point. Questions on any of that? Makes sense, I think, for the most part, maybe? All right, you ready for the quiz?
Oh.
It's worth 0 points, right? Actually, it can be worth as many points as we want, right? It should be like whose line. The points just don't matter, right? So what's the root node?
50.
50, good. All right, who's the parent of 23?
17.
Good. Who's the child of 72? 54 and 76, right? Who's the child of 9?
No one.
Nobody, right? 12 and 23 are what?
Siblings.
Children of 17 and their siblings. Good, both of them. Right? Internal nodes would be all the nodes that have children. So all the nodes minus what? 9, 14, 19, and 67? 9, 14, 19, and 67 are what?
Leaves.
Leaves. Good. Right? 9 has ancestors as we go up the tree. Right? 50 has, because the root node has lots of descendants, right? All the nodes of the tree are its descendants. Right? If I pick 12 as a new root, we call 12, 9, and 14 a what? Subtree, because it's a tree within a tree. Remember we talked about substring recently, right, with palindrome? Right, substring, a string within a string, subtrees, right? Tree within a tree. Anything else? Path is just how we get places. How many levels?
4.
4, and lots of edges, right? How many edges are in a tree? If I told you there were 15 nodes in the tree, how many edges would there be? Can you figure that out or not?
I think so, right?
No, because you don't know which ones are the leaves.
Yeah.
And which ones are the...
They could all be leaves for all we know.
Exactly. Just write a couple links down and nothing else.
Well, if they were all leaves, that'd be 15, right?
Right. 14 would be one less.
Yeah.
Because the God node, right? The root node does not have a pointer to it. All right, you ready to define what a tree is? You're like, I think I know it. Okay, let's talk about this. Right? A tree consists of nodes connected by edges, right? We have to figure out what nodes are, what edges are. And the properties are this way. Right? One node is designated the root node, meaning it has no parent. Right? And every node in, so every node, is connected from exactly one other node, where P is the parent of N. Okay? What this is really saying is that every node, right, is going to have, right, a parent. Right? And there's not going to be some circular where, right, this is the parent of that, which is then the parent of this, which then goes back, right? There's not going to be any circles in your tree. Everything's going to tree out. Right? A unique path traverses from every root to each node, which means that you can't have things like this. You can't have, right, node, 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 right? We think of these as arrows. You can't then, like, right, have arrows like that. Right? You don't get no circles in trees. Right? Every path, right, traverses from, right, is unique. But to get here is not unique because you can take this path or you can take what? That path. Right? And so we don't have a tree. Right? But every node is connected to another node in a relationship, right? Parent-child relationship. Does that make sense? Yeah.
So you can't have 2 parent nodes of the same child?
2 parent nodes, same child. No. Not with this, right? Because you would not have a unique path. So here's a tree that fits that definition. Right, some nodes, right? Here we're showing, right, some objects that have pointers. So node and pointers to other nodes. right? Does that follow the definition? One root node? Yeah, every node connected to its parent node, right? And a unique path to every node in the tree. Work? You ready for the recursive definition, which always hurts our brains? Right? So here's the recursive definition. A tree is empty. That's kind of funny, but basically, if you have no nodes, you have a tree. It's just empty. Right? So is a tree empty or consists of 0 or more subtrees? A lot of 0 in here, right? Empty, 0. But either there's no tree or there's 0 or more subtrees. Right? Let's get back to a tree. Right? Everyone good? There's a tree, but then here's a subtree. Here's a subtree. Here's a subtree. If you went down, right, these point to null, right? There's no tree there, right? 0 or more subtrees. Right? Some nodes are leaves, so they have no subtrees. Make sense? Why the zero's in there, right? And the root of each subtree is connected to the root of the parent tree by an edge. So when I look at this tree, right, here's a subtree, it's connected to, right, its parent by one edge. Here's a subtree, it's connected to its parent by what? One edge. Here's a subtree, it's connected to its parent by one edge. So that definition works for a tree. It's just a recursive definition. That makes sense? Right? And so we can imagine it look like this, right? We have a root and then we have 3 subtrees. Now we went into those subtrees, they could look exactly like this tree. Does that make sense? So they could have, right, if I went into this subtree, right, I could have a root node and then a subtree. If I went into their subtree, I could have a root node and a subtree. And that happens until what? You get to a leaf, because leaves don't have what? Children. So there's no other subtree to go into, right? They've made it to the end. So if you think about the fact that recursive algorithms always need a stop case, right? That terminating condition, right? When we get, right, to the end, right? And for us in code, these are still going to have pointers. They're just going to be what? Null. Right? Eventually we'll get to that null case, and that's when we know we've hit our terminating condition. We should go back up the tree. Questions on the recursive definition? Would what?
If you're going back up the tree.
If you're going back up the tree, well, if we do it recursively, the end of that is that we've popped everything on the stack. So that's what ends that. There's lots of different types of trees. Right? We're going to look at a binary tree. Okay, when you think of binary, you think of what? Ones and zeros, right? So they're going to have how many children do you think? 2, right? 2 children, right? Because it's binary. Parent can have maximum 2 children, right? So we call them left child and right child, right? That should make sense, right? Recursive definition is a binary tree is empty or, right, consists of a root node and then a left subtree and then a what? A right subtree, right? So a binary tree is a tree that has 2 children, right? A left subtree and a right subtree. Remember, we're saying subtree because it's a recursive definition. So if I go into that subtree, right? So if I go into the left subtree, either it's empty or it consists of what? A root node and a left subtree and a right subtree. If I go into one of those subtrees, then I look at that tree and I say, oh, it's either empty or has a root node and it has a, right? And we can do this all day. Right? Everyone with that?
Which child is the favorite child?
Always the left one.
Okay. Seems.
Obviously, look, my tree's been overloaded on the left side. Right? Favorite child. Right? This one didn't get him out of Thanksgiving. I know, it's cruel.
Escalated?
I'm the youngest of 4, so yeah, I was the forgotten child.
Do the right child.
I'm the right child, right? We don't like the right child. Do you remember when we talked about binary search algorithm? Just very briefly, I said the quickest way to find something is to take a sorted list, pick the middle, right? And then you can find out if it's higher or lower. And then you have, right? Because every time you knock off 50% of the thing that you're looking for. Does that make sense? Right, what we said, guess a number from 1 to 100, what number should you guess?
50?
50, right? Because then if I say it's higher, you've gotten rid of 1 through 50, right? That's the most that you could have gotten rid of, right? And a binary search tree is a way of basically implementing that search algorithm efficiently. Okay, so not as an array, not as a linked list, which we said linked list is really hard to do binary search with, right? But as its own data structure. And these are the rules. You ready for it? All the values in the left subtree are smaller than the root node's contents. So all the values here are smaller than the root. Okay? Conversely, all the values on this side are what? Larger, right? So they're all larger. Notice there is no equal. Okay? So there's no the same value. You only store the same value one time. So all the values on one side are larger, right? That's the right side, and all the values on the left side are smaller. Right? And then you can apply those rules recursively to all the subtrees. Right? So all the values on the left side are smaller, all the values on the right side are larger, but when I go into this subtree, all of its left values are going to be smaller, and all of its right values are going to be larger, right? So we just keep applying this thing, right? So when you're at any node, all the values to the left will always be smaller, and all the values to the right will always be larger. Any node in your tree, that's what needs to hold in order for it to be a BST, right? Binary search tree. So there's a binary search tree, right? If I take 8, 10, 14, and 13, are they all larger than 8? Yes, 3, 1, 6, 4, 7, all smaller than 8. Agreed? Now notice if I take 3, 1 is smaller than 3, so that works. 6, 4, and 7 are smaller than what? Or are larger than 3, so it works. But then when I get down to 6, 6 has 7, which is larger, and 4 that is smaller. Once again, all of those values, right, there's 5 of them, are smaller than what? Than 8. Does that make sense? Right, there's my binary search tree. All the values, right? So if I'm looking for a number, I start here, right? I'm going to guess 8, and then I go one way or the other, right? I'm trying to find a value. Right?
So the left side will eventually stop, and the right side will just infinitely get bigger?
Only because I picked a small number, right? But maybe I have negative numbers.
Oh.
Right? Yeah, we're going to get to that though. That trees can be unbalanced. They're a little unstable, like a lot of us in this class, right? So we're not going to write, luckily for you, right? We're not going to write balanced tree algorithms. That's what algorithms 3 is for. It's to write tree algorithms where it's balanced. So the tree doesn't get way heavy on one side or way heavy on the other side. For us, we don't really care. And we're going to talk about that though today. Ooh, you ready for this? You guys did terrible. I can say that with certainty. You guys did terrible on the test when it came to what's more efficient for what, right? Linked list or an array. Don't know why you did so terrible, right? But you did. Everyone else is going to beat you up because you're the one reason I didn't just give you all the points. No. All right, so let's talk about that plus trees, okay? So for insertions, let's just do the linked list and the arrays. For insertions, the linked list was constant time. Remember, you just took the node and you just updated some links, right? That's the constant time, right? For an array, when you inserted, you had to shift, right? That's why it takes linear time, because you might have to, right, shift all the elements, right? And so that's the end. Does that make sense? Right? I don't know why, once again, I don't understand why we got it wrong, but we did. Same thing with deletions. To delete something in a linked list, you just update the links. To delete something in a vector or an array, you have to what? Delete it and then compact. If you deleted the last or the first thing in the array, you're going to have to compact everything. So it takes n time, right? Because there could be n values that you have to shift. Indexing, which is getting where you need to go, right? Linked list took linear time because you had to go through the whole list to find what you're looking for. And an array, you just say, I want to go to index 5. And you go directly to index 5, right? So there's the benefit of arrays is the indexing feature. Resizing in the linked list, there is no size, right? We keep adding nodes until we run out of memory. So we can do as much as we want. and arrays, they're linear, right? Because once I've run out of space, I have to create a new array, copy all the values over, make it bigger, right? Blah, 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 you did that, right? And then finding an element, and this is new for us in linked lists and in arrays, it took in time, right? Look at the first value. Is it the right value? Yes or no, and then go to the what? The second value. Is it the right value? Yes or no, go to the third one. Does that make sense? Okay. You'll notice that linked lists and arrays, they kind of switch back and forth, right? Some things are constant time, some things are linear time. Constant linear, constant linear. Remember going back? With trees, you don't get any of those. What do you get? You get H's for everything, right? Which, regardless of knowing what the heck H means, you can see that the tree is more general purpose, right? It's like, well, I'm kind of good or bad with everything. We don't know what H is, so we don't know if it's good or bad, right? But they seem to be the same regardless of, right, what we're doing, right? Everything seems to be the same. Does that make sense? Whereas linked lists have very specific applications, constant time, and arrays have very specific applications, constant times. Where trees are like general purpose, work for anything, right? Which is why we probably use them a lot as an underlying abstract. You want to guess what H is?
Hamburger.
No, that sounds pretty good though.
Hamburger time.
So the number of splits, no, but you're on the right track. Remember, trees are arranged in what, a hierarchy? Right? So there's a height to the tree. Yeah. H is for height. Right? So H is the height of your tree. Now there is no guarantee how high your tree is, because we were just talking about, right, a tree could get really unbalanced where there's a lot of nodes on one side. So the comparison of H and N depends on the best and worst case of your tree. Best case is your tree is balanced, same amount of nodes on one side versus the other side. Balanced tree just says that at most, you're not more than one level different on both sides of your tree. Okay? An unbalanced tree means it's more. Okay? Worst case, what do you think a tree looks like? Right, this is technically a balanced tree, right? Right? There's only one, between my leaves, there's only one level difference. Right? Worst case, it's going to look like what? Root node, if I had 4 nodes, that points to this one. I mean, it doesn't matter which way. This points to this one, and this points to this one. Is that my worst case? Right? So there's my worst case. What does that look like? It's a linked list, right? So worst case, the tree is a linked list. Right? Which makes, right, HBN, so it's no better. Does that make sense? So worst case, it is a linked list, but worst case we're hoping doesn't happen very often. Better tree structures get rid of the worst case. And that's why here we said resizing, I say no need sort of. You don't need to ever resize a tree, but sometimes you need to balance a tree. Right? Rearrange the tree to keep it balanced. Right? That happens every once in a while. So there's my worst case. Right? Best case is it's balanced. Right? So this is tree is balanced, right? The depth of the subtree is different by at most 1. You basically could just say the leaves of the tree differ by at most 1 level. Okay? If 5 had a child, my tree would be what? It'd be unbalanced, right? Because the leaves would be on 3 different levels, right? So it's not balanced anymore, which makes H slightly more inefficient, right? Makes H worse. Does that make sense? All right. That's all I want to say about that. Okay, let's talk about how we get to all of my nodes, right? So in a linked list and in an array, we have the idea of traversal, right? Array, it's easy. Start at the beginning, for loop, get to the end, right? Linked list, not so hard. Start at the beginning, while loop until I hit null, go to the end, right? They're easy because, right, both those data structures are what? What do we say? They're linear, right? There's only just a before and after. What came before, what came after. Trees are not linear. How do I start at the beginning and get to the end? Where is the end? Right? There's lots of ends, right? But I want to get to all of my values in the tree, right? Traversal. So we got to talk about tree traversal algorithms because they're not just our simple linear loop algorithms. Does that make sense? The good news for you is that these algorithms are going to be what? recursive, meaning that they should be easy once you write them correctly. And if I give you correct pseudocode.
It's easy after you complete it.
Yeah, exactly. If you write trees correctly, right, then the time complexity, right, not linear and not constant, right, you get log n, which is actually really good. So log time complexities are really good. So trees become actually really efficient. All right, so 2 ways to traverse a tree. We have depth first with a D, depth first, and we have breadth first with a B, okay? Because those are fun things for me to say, right? Depth and breadth. So depth first says we go down the tree and then go back up. So we go down subtrees, come back up, go to the next subtree, come back up, go to the next subtree, come back up. This is the easier way of us doing it because we have links, right? We have links to get down my tree and back up. Breadth first visits nodes on a basis of level, right? So that would be, right, level 1, then what? Level 2, then level 3, and then level 4. Not as easy because, right, as my tree gets larger, if this had, right, if this was actually a node, right, these nodes are on the same level, but they don't share the same parent, right? They share the same what? Grandparent, so it gets a little bit harder to, right, output things on that level. So depth first is easier, breadth first is harder, so which one am I going to make you do?
Depth.
Yeah, I'm going to make you do depth. Isn't that nice?
Could you, for breadth first, could you keep track of how many ancestors each node has and then just use that?
Yeah, but you still have to get right back up, right? You still have to figure out where you're at. All right. So not only are we going to do depth first, which is easier, that's good, but I'm going to teach you 3 algorithms. Okay? Preorder, in order, and post order. Because I can traverse the tree, but I can traverse it in different ways, meaning that I can, right, visit the nodes in different orders, but still get to every single node in the tree. Does that make sense? So, once again, in an array, I start at the beginning, I go to the end. But imagine if you did every other and then came back and then did the others, right? There are ways of getting to every node that's different, right? And these are 3 ways, and the 3 common ways of doing it in trees with depth first. So let's look at preorder. Preorder says you visit the root, then you go left. Go left means you traverse the left subtree, and then you go right. That means you traverse the right subtree. Okay, I'm going to hammer this on Wednesday, but when I say go left or go right, I mean call the same algorithm, right? So if you're in the depth first preorder algorithm, you're going to call that same function. You're just going to pass in the left subtree, or you're going to pass in the right subtree. So you visit the root, you go left, and then you go right. So you visit the root, and then you go left, and then you go right. So if this was my tree and I was visiting in a pre-order condition, right? What's the first thing I do? I what? I visit, I go left, and then I what? Go right. So if I start at the root and I visit, what value is that? Right? So preorder says we visit F first. Does that make sense? And then which way do I go? I go left. And I go left before I go right. So I go down to B. And now I apply my algorithm to it recursively. So I'm at B. What's the first thing I do at B? I visit. So what do I output?
B.
B. And then I go what? Left. And so I go down to what? A. So what do I do? I visit. So what do I output? A. And then I go what? Left. Can I go left? No. So, okay. Now I go right. Can I go right?
No.
No. So I'm done with that algorithm. Agreed? Which means that I'm done with A, and I pop back up to what? B. At B, I've already visited, and I've already what? Gone left. So the only thing I have left to do is do what?
Go right.
Go right. So now I'm at D, so I visit, and then I go left, so I'm at C, so I visit. Then I go left, No. Go right? No, so I go back to D. I've already visited, I've already gone left, so I go
Right.
right, which is E. So I visit, right? Go left, no. Go right, no. So I'm done with E. I go back to D, and D I've already gone, visited, gone left, and gone right. So I go back to B. I've already visited, I've gone left, I've gone right. So I go back to F. I've already visited, I've already gone left, so I have to go
Right.
right. How do I get back up the tree? How does that magic take place?
The plates coming off the stack.
The plates come off the stack, right? The function calls pop off the stack, which brings me back up the tree. Does that make sense? Right, so I don't have to worry about that. The plates will come off the stack automatically. So I'm at F, I visited, I've gone left, so I've gone right, so I'm at
G.
G, so I visit, can't go left, so I go right. I'm at I, so I visit, can't go left, or actually I can, so I'm at H, I visit, can't go left, can't go right on H, so I pop back up to I. I've already gone left, so now I go right, can't, so I pop up to G, I just went right, so I pop up to F, I just went right, and what? I'm done. All right, we're done with it. So I should have 3, 6, 7, 8, 9 values, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Does that work? Right? So that's depth first, preorder. Okay. If I were to ask you this question on the test, which I will, one of them, preorder, in-order, post-order, this is what I do. Okay. I draw a line around all of my nodes. Everyone see that? The line goes around all of the nodes. Okay. In preorder, you visit the node first. Okay. So the dots are on the left side of my nodes. And we're good with that because you visit it first. So you follow that line and you follow the dots and we follow what we did, right? What do we visit first? F, and then I keep going and I visit what? B, and I keep going, I visit A, and then I visit D, and then C, and then E, and look, this is all the popping off, right? And then I visit G, and then I, and then H, and then everything else pops off. Was that? All right? Anyone remember the comic Family Circle? You guys too young for that? You guys ever see this? Family Circus? Right? They would draw these every once in a while, right? The kid like runs around the house, right? They show them where they want. That's what I think of when I think of these algorithms, right? Just draw the dashed lines around the full thing, right? And put the dot. And you should be good to go. This is how my kids get around, by the way. There are no straight lines in my house. Okay, so that's preorder. What do? You visit, then you go left, and then you go right. Okay. In order says you go left, right? So this time, instead of that, we go left first, and then what do you think we do?
Is it?
And then we go
Right.
right. So where do we start? We start at the root, but do we visit it? No, we pass by it, right? And we go which way? We go left. So we're at B. Do we visit it?
No.
No, we go what? Left. So I go to A. First thing I do in A is to do what?
Go left.
Go left, which I can't. Then I visit, and then I go what? Which I, so I pop up to B. I've already gone, so now I, right? And then I go, no, right, yeah. You're like, where am I in this thing, right? So I go right, I'm at D, but I don't visit D. What do? Go left. C. And then I go left, which I can't. So then I visit. Can I go right? No, so I go back up to D. I've gone left, so now I visit, and then I go right, so I'm at E, and then I try to go, okay, which I can't, then I visit, then I go, right, which I can't, pop up to D, I've already gone left, visited, gone right, so I pop up to B, I've already gone left, I visited, I've gone right, so I go up to F, I've already visited, So I've already gone left, so now I visit. And then I go right. So I'm at G. Can I go left? No, so then I go right. So I'm at I, and then I go left. So I'm at H. Can't go left, so I visit. Can I go right? No, so I pop up to I. I've gone left, so now I
Visit.
then I go right, which I can't, so I pop up to G. Already gone left, visited, gone right on G, so I go back up to F. So I've already gone left and visited, and now I've gone right, so I'm done. Why is it called in order?
Because it's in order.
Because the output is in order. If, right, remember we're dealing with binary search trees, which this is, right? If you think about it, all the values to the left of F are, right, beginning of the alphabet, and all the values to the right of F are what? Later in the alphabet, and that rule holds, right? A comes before B, D, C, and E come after B. Does that make sense? So this is a binary search tree. If you apply the in order algorithm to a binary search tree, you always get the values in order. Does that make sense? So, which is kind of important, right? Because as I add values to the tree, I'm going to put values on the left side and the right side, right? But if I want to get the values in order, because I'm keeping in order, right? In order is the way to go. Notice preorder is all jumbled, right? But in order works fine. Right, and there's my family circus drawing.
Is preorder faster?
No, this is the same. Time complexity are all the same. So it's just how you visit. Right? Because they're still going to get a function call for every single subtree root. Right? It's just when
Nothing saved or spared or whatever.
Right, exactly. So notice now the dot's not on the left side of the circle, it's on the what? The bottom. Because we visit in the middle, right? Before we visited first, so the dot was on the left side. Now we visit in the middle between the two function calls, so it's in the middle. And then the next time it's going to be where do you think? It's on the right. We're going to talk about that in a minute. But this should work, right? Because as I follow my dashed line, right, first one that I visit is what? A. It's not the first time I've seen these nodes, okay? Everyone keep clear with that? I started at F, so I've already seen F, but I did not visit. I just used it to go left. I've already seen B, but I just used it to go what? Left. Now I can't go farther left, so now I can visit it itself, right? So A, B, C, D, E, F, G, H, I. I hadn't seen the alphabet sound. Which I guess they changed. Did you guys read about that? No. Apparently element OP is a little hard for kids, so now it's still L, N, N, O, and then anyways. Look it up. Kids these days, I tell you, man, just handed everything. Right?
Snowflakes.
Element OP, I just thought that was like one big letter, special letter. Mm-hmm. Yeah, so anyways, apparently a little too hard. I can't imagine what I'm gonna have to teach like in 20 years. Here, I'm just gonna write the code for you on the board. If you could just copy it and then turn it in, and then we'll just move on to the next lecture.
You should just do that.
Hope I'm retired or dead by then. I probably won't be either. Hopefully not. Anyway, post order, we go left, then we go right, and then we visit. So please note, always go left, go right, right? It's never go right first and then go left. So we don't change the order of go left or go right. We just change the order of visiting. Do I visit first? Do I visit in the middle? Or do I visit at the end? Okay. Which means when I see my node, okay, let's talk about this. When I see the node, it is the last time that I will see it. Okay, what do I mean by that? Right? When I see B, I will not visit B again, as far as like remember my function calls. Because if you think about it, preorder says, okay, great. I saw B one time, I output the value, right? Then I go left, and eventually I come back to B. So that's the second time I saw it. And then I go which way? Right? right, do my stuff, and then I come back to B, that's the what? The third time I saw it. So I always see a node 3 times, assuming that it has children, right? If it doesn't have children, I don't really go down the subtrees. But you always see the node 3 times. Preorder says I visit it when I see it the first time. Interorder says I visit it when I see it the second time. And postorder says I see it the last time, right? So I will never see this node again, right? I'm trying to help us out. Where do you think a postorder algorithm would be useful? When I'm deleting. Because if I'm seeing you for the last time and I don't delete you, what do I have? A memory leak? If I delete you the first time I see you, then you can't get to the sub-children. If I delete you the second time I see you, then I can't get to half my children, right? All the right children, because we don't like them. Remember, we already talked about that, right? So postorder is a great algorithm for deletion because this is the last time I see you, right? I've already gotten rid of all of your children subtrees. That sounds terrible. That's fine. I've already gotten rid of this subtree, and I've gotten rid of what? This subtree, so now I can get rid of B. Make sense? Deletion's never good when, right, the verbiage we use is like parents and children. It's just not good. Well, there it is, right? It's on the right side because, right, I start at F, but the first thing I do in F is to do what? Go to B. And the first thing I do at B is to go to A. So the first thing I output is A. Right? And then I can't go, well, I've already gone left, gone right. So then I visit, I come back to B. It said go left, and then it said what? Go right. So I go down to D, and then it says go left, so I'm at C. Can't go left, can't go right, so I output C. So I go back up to D, I've gone left, now I go right. So I'm at E, can't go left, can't go right, so I visit. Okay. Now I'm back up to D, and once again, I make it to D, and I've already seen what? Both C and E, right? Both of its subtrees. I've seen all the values in those subtrees. So the last time I see D, right? So I output it. Pop up to B. I've gone left and I've gone right, so what? B, I go up to F, I've gone left, but I haven't gone right. So I pop down to G. Go left, no, go right, I. Go left, H. Can I go left anymore? No, can I go right anymore? No. So I can do H. Pull up to I, I've gone left, and now I go right. There's no right, so now I can visit. Up to G, I've gone left and I've gone right, so I can visit, and then I go up to F, I've gone left, I've gone right, and I can, right? It should make sense that the last value that you visit in postorder is the root node, right? It is always the last value, because basically the algorithm says is visit the left subtree, visit the right subtree. Once I visited both, right, visit the root. Right? Meaning that you've seen all the values on the left side and you've seen all the values on the right side. If we're talking about deletion, you've deleted all the values on the left side, you've deleted all the values on the right side, so now you can delete the left. Does that make sense? Let me get back to our family circus. Anyone know HTML? Right, a couple of you poor souls. I won't say that because I teach the class. Not all of you taking their time. But in an HTML document, right, HTML comes first, right? Inside of HTML, we get head, right? Inside of that, we get things like meta, right? And then we close our head, and then we get body, and we get a bunch of stuff in body, and then we close the body, right? And then we close the HTML. And you can store all of these, what they're called elements in HTML, you can store them in a tree-like structure. In fact, we store them in a tree-like structure, right? And so you can create the structure, but then to, right, recreate the structure as code, right, we need to apply a traversal algorithm to them, right? And so the question is, which traversal algorithm would take my tree and write my HTML? I'm not gonna give you the answer, remember? 20 years from now, I'm gonna give the kids the answer, but today I'm not gonna give you the answer. What do we think? Preorder, right? And it's pretty obvious that it's preorder, because preorder says what's the first thing we do? Start at the beginning, right? Visit the root, right? F was my root. A's were not my root, right? So if I want the root to output first, it's always what? Preorder. So even if you don't understand anything else, you just know I visit the root first, and he wrote HTML first, so has to be what? Preorder. But it works, because what do? I visit the root, and then I go which way? Left, which is head, and then I visit head, so I wrote it on the board, and then I go what? Left, so I put meta inside of head, can't go left, can't go right, come back to head, and then I go right, title, right, got written, and then we're done with head, right? And then we move on. All right, so it's preorder. Did you know you could take like mathematical equations and put them in a tree-like structure? Right. Look, here's my equation. 5 plus z divided by -8 times 4 squared. We take that and we can put that in a tree-like structure, right? Each of the operations, right? And then we could use a traversal method, right? Which traversal method would I use to recreate, right? With precedence, right? One of those. Which one?
Order.
You just say order? They're all order. Preorder.
No, I'm saying like in order.
In order, yeah. Right, once again, it becomes obvious because when you look at the root node,
It's not
is the
right.
first thing I output a star? No. Is the last thing I output a star? No. So that preorder and postorder are gone. Right, so it has to be what? In order, right? Before I can multiply, I have to what? Divide. And before I divide, I have to what? Add. And I have to add what? 5 and z together. Once I add those together, I can then divide them by what? -8, which is the left side of the print. Does that make sense? The precedence is built into the tree. It's kind of cool, right? I take all of that operation and I multiply it by something, right? In order says left side first, then me, then what? Then right side. So I'm going to multiply it all by what? 4, left side, right? Squared. Kind of cool? Trees become really useful, actually. We use them all over. Questions on trees? They make sense? This is your last easy lab of the semester, okay? So enjoy it. Take your time, create your node, right? Create your left child and your right child. Because remember, we're creating a BST, right? Binary search tree. So we're going to make a BST node and a BS tree. All right? BS stands for what? Binary search. All right? It's a real tree. It's not a BS tree. Okay. So today you're just going to make the BST what? Node, right? And it's going to have contents, just like our linked list nodes had contents, right? An integer, right? And then it's going to have 2 pointers to BST nodes. Right, one to the left child and one to the right child. So I recommend that's what you call them. Okay, don't call them like next node and previous node because that's right not what they are. Don't call them next node and next node because that's not what they are. Right, they're the left child and the right child. Or if it helps, and for some students this helps, call it like left subtree and right subtree. Right, either of those definitions are going to work. Left child, right child, or really, it's a pointer to the left subtree and a pointer to the right subtree. So both of those definitions work. So depending on how well you're doing with recursive algorithms, you might want to call it left subtree and right subtree. Does that make sense? But basically, you're just writing your DL node again. Because the DL node had what? Contents and 2 pointers, right? But we're naming them differently because next class, we're going to learn the algorithms to create the tree, right? And then we'll organize them in a tree lecture. Questions there? Remember, all the algorithms end up being pretty short because we're going to write them recursively, right? Which makes them a lot easier for us than writing them iteratively. And adds a bunch of function calls to the stack, right? Because once again, we're visiting 3 times, right? So we see it a lot. Good? I'm gonna do grading this week, so just realize that if you don't have labs up to date, you don't have assignments up to date, I will still take them up to the point where I grade them. Which Tuesday, tomorrow, I'm gonna get like probably at least your assignment 2 done, maybe your assignment 3 done. Right, so just realize the day of reckoning has arrived. Almost. Right?
Reckoning for assignment 2.
The day of reckoning for assignment 2 has definitely arrived. And I would say by Friday, the day of reckoning for assignment 3, and probably at least all the labs up until now has arrived.
Friday.
By Friday. By Friday, but I might grade it Thursday. You know.
Is this for CSCI 31 as well?
Mm-hmm. I'm probably gonna intermix them. So I'll do an assignment for this, and then I'm done with code. So, fluffy HTML. I need a palette cleanse that over on some of those. Exactly. Although the key is, I guess, if you just come visit me in my office, then I can't get my work done.
Or you can just give everyone like.
So one person has to take the hit to let everyone else catch up. Right? Yeah, Missile could talk my ear off all day. You can just hang out. We'd be good. That's right. Yeah.
What's a
You're all
pointer?
caught up, so it works out perfectly. I'm not losing. Anyway, so those are your other options. If that happens, I might hide somewhere else on campus. You see Luke today? No, I don't know. Right? Like hiding under my desk.
I'm thinking I'm cold with my beer.
That's right. You put like a little tile on my keychain or something.
Or like, just use it by people's like interaction. I found something this morning.
Now we give you a mug. It has an.
Yeah, I think see, that's smart. That's smart.
It's a really cool mug.
It's funny, like you create like complicated app that tracks you down.
What is this Arduino in my pocket? I like it. Right? All right, good. Questions? No? Are you going to enjoy your last easy lab? No, you're not?
Not really.
I bet you can get done in like 20 minutes.
You make a stack.
Can I make a stack?
Or is there only one stack?
There's only one call stack.
Like people literally treat the virtual just to get a plan.
Oh, yeah. And they made their own like stack algorithms inside of the.
Like reference a stack, and I've never seen that done before.
Yeah, that is weird. You can reference. There are ways to kind of get to the stack and what's going on. You may write a stack at some point this semester, because a stack is a specialized linked list, and a queue, which we talked about as well, is a specialized linked list, right? Everything for the rest of the semester is up on Canvas as well, so if you just want to like bust out all the labs and all the assignment and just not show up for a couple weeks, I guess you can do that. That's up to you. Okay. This one. I wonder if there was maybe that was.
Yeah, I should. Second day.
Yeah. The road is back to the second or just the trading character tree and faster to end up to the middle thing.
I see.
I was looking at this.
How are we gonna do this? It's on the way.
Yeah. It's not right, that's how it gets too late before you have to leave.
No, I know, we're gonna go 2021, 22, so this week. No, boy, yeah, it's actually really fun. Yeah, because he's got, we do arms, but then he's got on the boards.
Okay, so yeah, so it's incredibly like worded weird, but this point, the no trailer is pointing to iteration, right? So trailer is actually means pointing to iteration.
It's not, well,
So it'd be, it wouldn't be equal, it'd be trail, arrow, set next node, inside the parentheses, higher arrow.
I can just, you like, just pull over there, right? If there's something there, temporary pointing to it, have them move forward. And if there's and move forward and it's not null, you go back, array.
Like 4 or 5 different implementations. The one that really was interesting was right outside the node, the struct node. They defined this thing. They would type that null.
Outer
It
arrow.
was defined over. What is that?
So a type dash just wraps, you can basically create types.
It's probably gonna be like get next or something like that.
So if you hit right int, you could type that out.
No, you got this, right?
I think with that,
It might matter for you.
Yeah.
He calls that, so that has the match.
I try to like take his functions and try to implement them.
Trail set,
Right.
trail set next
And it's
node.
just tough because I didn't know where to point it was. Because I used to like, you defined it outside globally, so now it had no pointers in it.
You got it, man. Close.
Like, shit.
Nice.
It was weird though, because he kept making up new pointers out of that one.
So you're proving to a decrement.
Well, because it's just
You need a decrement out of your.
So if you say,
He used it to create a bird pointer, he used it to create like so many different.
right, well, if you like type that, right, let's say you type that real node
Literally, that's what he said.
star as PTR, something like that.
That's, yeah, okay, so he literally did that.
So then, when you say PTR previous node, right, that's the same exact same thing as VL node star. So it's literally just an alias. So, I don't want to write this, I want to write that.
So,
That's all that's.
so if I just.
What is this? What is it?
Type that. This is wrapped up in the type that. This is.
Yeah.
What it is. I usually. I started reading a lot more. I started reading a lot. This is just like really. Next with.
It's 1.7.
You don't have multiple lists. You have multiple lists. You sure you're looking at the right one? 27.
I might.
Make sure there's not a whitelist here. It shows over here what you have selected. Scroll up.
It's probably close.
Keep scrolling.
It's probably in my 19.
I was gonna say, it's, when you have this selected, it should show you over here what it's highlighted. Like, click that again. Now scroll up here. Oh no, scroll up. Keep going. Scroll up.
I think it's 18.
That's just super weird. On mine, it shows exactly what you're looking at. Like, it'll highlight it. Interesting. It's like you're not doing it right now.
So the ampersand right there is by reference, right? It's just a return by reference, so if you call the contents, it returns the point. It actually allows you to call this from it's a reference to that area. So it's a way of, because we didn't write, right? We didn't write a sentence. This is right? But basically that's what it's
Let's show you what you don't.
We make it because technically pointed on that side.
I don't know why sometimes it parts.
I found, I mean, I might be wrong. So, if your cursor is all the way to the left, now what if you're in the middle of one of those two spaces, when you press tab, it only has one. I know that. You have to use that. There's an odd number in there.
That's what a lot of people say, how to
And maybe, maybe harder, but like this hard.
Okay, got it in work.
Yeah. Okay. Did you already have this?
Yeah, I did, but that's not the problem. I pass all the steps now.
Because my problem was, I wasn't setting it as less than or equal to the contents.
Like create a curve. Oh, yeah, you create a curve piece, and then what I created was. Iterated was iterated trailer.
Oh, wait, no, I still
Right, let's not line up, it's not finished. Right, with 5, and then CSCI. Not bad. Nice. One more word.
Oh, wait, I'm looking at the wrong one.
But then with this less work,
And it sends the input back to the multiple, so it returns to the all. So, we're stuck. So, it's not tutorial one, right? You want to no. So 5 factorial is 5 equal to 4. So you can run other because we can do say this times the next factorial and then use it for this one.
Okay, so close it works, right?
So you start go until you get to one and you say factorial is 0.
No, this is flowing.
So you
Flow is
this one is 1. You can not even point if you can solve it through 1. And then go back.
No, I don't see what that is. Yeah.
I haven't done So you have the right force, and this is if you're after you start
Because I think
so that's this goes like this is like that. So this goes in Europe and at least it's supposed to be good. I started training those to start doing. Essentially, if you just
it's like it's probably yesterday.
passive, one minus one, out of 0. If I one, so then we just go back to we just wait until somebody so then we return back to yeah, and eventually it's 1 out of 4 factorial. So it's pretty much
That's a weird. No, I didn't show that last argument.
these two
It's very message right here. Which is right here. It's asking for use also for 5 ultra, which is what's not that long.
you guys remember what the allow was it for displaying times value?
Oh, it's really, it's,
That was one thing.
I think it's 3 or 4.
Yeah, so
Yeah, it's real early.
That stopped at like 8, something like that.
So you can use your person. Well, remember that previous instances of it.
as far as you want to go, right? So you say, I want to go for this far. And you go, okay, and it does one, and then well, this is this. So.
But yeah. You said you looked at one through 8?
I went across so 14 to 8.
Oh, I see.
Place.
And I stopped because I thought I was going too far.
No, it is super early.
1, 2, 3, 4, 5, 6, 7. So we're
It's
gonna do
making-
something. It's like a thing.
I mean, I think it's
It's
fine.
Well, then it is.
It's super early. Literally just had to look at it.
We need to.
Yeah, it is fine. Just like prepare for the play.
Okay.
Depends on both. We can keep track of both of these. So, here's page 7. So. It's not 0, it's not 1. So, we're at the 7th spot.
And now it's a
Spot and the 5th spot. Right, we gotta figure out both the 5th
So I
spot.
think it's
Before we can figure out 7. We gotta know what these are before we can get this. And then,
So I have like this entire section here, pretty much where I pulled in else.
get 5.
Here's the else,
Also
wrapping the
some.
entire else.
And
Question
then,
I'm
so then we
making
run.
is first check and see if there are emotional,
So 7.
trending
So now
diagnosis.
solving.
This, the problem is I'm wrapping else inside like all of the.
Because the else is just the alternative case of your head being core. So if your head is not else, which is fine.
This says, the unique else and harmony for you to measure in there. Back first,
Make sure we listen to something.
Click this, the inside of it.
So what this reaches 0. This will also.
I see what you're saying.
0, 1. But it also.
It's saying start a new line. Just go to right before that end. Get rid of that space that's right there. And press enter. That's what
We
it's
able
saying.
to figure out this one.
That should get rid of that.
This one helps it.
But it's saying it shouldn't be on the same line
So
as
we
the
can
ending
do
of another.
very.
But wasn't ending there.
It technically was, because this while ends right here. So if you have an if right after on the same line, it thinks that you're trying to do it also.
Alright, I will take care of it.
Yeah.
So, yeah, you're starting it.
So, essentially, you call, until you get to a call that can be translated, which is your base case, it's the smallest you can make. And then those calls
Have
start
one
returning
given
each other.
function that is, that's into skip a line. Or is it that's default in the tab?
Essentially, those are not variable, and you actually have to break out its case. So, this 5 is essentially, this is like, this just says, our products, you know the solution, find our products. So, it's pretty hard to do. It's always going to be difficult.
I really,
But you do have to know.
okay, so I need to, so I think now.
Really helpful to draw these out. So this is really good, but then you go to the next one, and then just make sure you have an answer to which one goes back to. You can solve that by it's not very fun, so we have well, I guess really annoying when it's not word, so we got word is probably, so just shut down the words.
No, like you'd be able to use
I saw a little. That's some weird.
Okay. I think you have to create a template. I don't know. If it's not there, just create it. Yeah, I'm here to try to check it out.
But check for that.
Like for no, not you mean like for Oh, you mean like we're here?
Yeah, you know, like.
Well, yeah. I mean, like that has the first one has to be an address of a thing of type T. I mean, that has to be that can't be side. You know,
So what you did is you went to a lab file, just change.
I don't believe so. I might have. I don't quite recall that.
True all the way through.
No, I don't think so. I don't think I have to change anything. I just the initial value of that. You just got to keep. Yeah, no, I
You just had to keep track of T.
Yeah, where it goes because it's not everywhere.
A little bit different.
It's just only the ones that are actually.
Yeah, that's right. Yeah, values that actually.
Same idea.
I'm trying to.
Same idea. We break the race cards down.
Not everywhere. Just yeah.
See where the.
Or the parts that shouldn't change, should not.
Well, to be honest, most of your stuff should be designed to work with it without changing anything inside. The only, like I know this one had to
Okay, we're gonna
return.
break them down into smaller pieces. We're gonna take a submachine.
That,
So we're gonna say,
Well, what I was just asking is, did you change?
we're gonna do that submachine. We're not gonna try to solve the entire thing. We're gonna break them into
I just literally just change everything over to T.
So we can solve it down.
Arrays.
That.
It sounds like something was recommend something, so I think it's just committed.
Hello?
My file and all these cores.
Oh, yeah, it's just a 2 dots. Dot does like everything. It adds the folder and I think the subfolders, but not to do everything.
I just wanted to just one down on the instructions.
Really? I don't think I've ever done this.
Hold on. This is get add dot.
Give me one back. But I've always done it sounds like a.
Oh, nice. Is that a gaming one?
It's, yeah,
Or a can game? It looks like
it can be just the right.
the neon green maybe.
So, I guess one step at a time. If there's, I was trying to figure out if I can go online, but like you do have to. But, anyway, so I tried to do it individually and that came up with all kinds of weird errors, so I found online you could do something similar to that.
Yeah.
But then I have to declare node and their class or something.
You don't have to declare a node, so you do that, and then when you write them, like down, so you end up actually writing them all on the main file.
Oh.
So down here, you would do write it. Yeah. Just like, it shows up everywhere. And then you do P, S, T, node, and T, and then T goes weird now.
You could like.
I see that's declaring the type of BST and
They're saying that it's templated, and it says the type of this tree is of the same type. So basically that type can operate.
and then so you don't need to use it everywhere like in here.
Not in here, but all of yours is all of the same split type into you.
Oh, I see all my declarations on the H file. I mean,
Yeah, although you won't write them as you
only the ones that are templates?
Yeah, which they're all. Your whole class is templated. Every function deals with this member variable.
Oh, I see.
So the whole class is templated. So if you go to, like, if you go to.
Yeah, do that from there.
So you can see how it's like, you know, it's like.
Here, so that means we go to the top, right? Those things that you're on
Yeah.
Well, that's what class names are, right?
Yeah, but then if you look at how.
Oh, I see.
Right, the class name is simple, which is template type names are equal to simple. The T, and that's every single one has to have.
Every constructor.
Every, not just constructor, every.
Oh.
This isn't a constructor, that's a.
I see.
Every function has it.
And it's inside the H file.
Yeah, you're gonna write inside the H file.
Okay.
Well, just remember that, like, when we use the ampersand by reference, it's just, it works, right? We don't have to do anything
So that's
special.
for some form.
So when we return by reference, then just return content, so you have to have the right hand.
Same as the
That's what we
previous one.
learned in,
Those objectives. And we're gonna talk about why we have two.
You know what it's not for?
Yeah.
So yeah, there's gonna be some slight renaming
What?
involved.
I was just wondering, there's from the same thing.
It pretty much is, yeah. It's just gonna be renaming stuff. The bestseller.
Right, so then you just can't say it. So you have to start with greater than equal signs. Right. I'm making it and that's like, and that automatically.
Yeah.
No, I was trying to remember the lunch we learned about
I'm not gonna say that part, because it is always false. It never works, right? Because it never lets them do it. Gotta work on our assignments and what says. Pick a manager, an assignment, and you compare it to less than 0. By definition, it's less than 0.
Yeah, it's always.
Let me click on my access, I'll like modify everything. I'm like,
And now you know it again, right? It's all give you a test, right? It all goes away.
I just asked them about the rest of it, you know, that unit and then listen to them now.
So like, the destructor
Uh-huh.
would not need to be in the H file because it doesn't like use the template.
No, the class is templated, so every function uses the template.
So you even need a CSCI file? Oh.
You won't write it. You'll, and that is only because templates and compilers, and the compiler sometimes gets weird, so we write everything in each element. Make it easier for the compiler. It would be better if we separated them, but the compiler sometimes freaks out. We don't write it all.
That's your executable. And that's,
No. Because then by reference just does it automatically. The only reason we do it by reference is because I need to be when I traverse the tree, right? So if my function takes me here, if it's by value, I don't have access to this, but I want access to this. That's what class matters.
It's true for the tree, it's generated just the H file. Oh, mistaken.
No.
So what it means by that is, no, but what it means, so normally your link list only has one pointer pointing to the next node, right? That's a single link list. A double linked list means every single node not only has a forward pointer, a next node pointer, but also a previous node pointer. So that's what you mean by doubly linked. So that's the only difference, you're just adding a previous node. So that, yeah, you would change that in node. Which you would just add. Should the recursive parts like be inside of like a separate function, like say for like delete all, like delete all the values?
Yeah, so what's gonna end up happening is we're gonna have one public and one private function. The public function is the one the user calls, and that starts the deletion, let's say. And then you'll call the private one, because the private one needs to know what you're deleting, so what root node. Because it's recursively from the root node, and then to the subtree root node, and the subtree root node. So our public one starts the recursive process.
Okay.
So you're gonna have two for every single one, but the public one probably won't have any parameters. The private one will have.
I would love to just say the public, the private one.
So I'm outputting this because data is a two-stream actually. So if I output it, you're going backwards on forwards. So like you guys can see why you're backwards looking on forwards. And all of a sudden, the two pointers have to be different. Translate So it looks like when you push front, you have to do back. The push front. The push front says to create the new node. Point the new node to the front. If the head is null, then the null has the first node goes down. Now, if head's not null, meaning I have one node, but this new node, right? And right now you say point this one, right? So the new node comes forward to this node. But now every node has one forward back. Right? So if I push in a new node and it points forward, what does it point to? Well, forward as well, but what else do we have? Every node has one. Forward and a one. So what does it have to have? Right. Where does it have to come back? What is it? This was the original node. This is the head. Right. New node comes in. We're going to come forward to this node, right? Right. And we do that so long as the head's not null. So we say else. Well, the new node is here. This is the old node, which is currently head. Right? And the function starts. We don't have to count it. This is head. The new node comes in, we point it forward. New node comes in, we point it forward, right? Because new nodes are already pointing forward. This is what's written. So what right from a 1.2% to right, still is, right?
Oh, still.
Because not until line 27 where we said head equals new node, does that pointer change. So it still is head. So it's still the head node, right?
No, you say, arrow.
So something here. Push front, two things push, goes forward, great, goes backwards, great. Okay, now we get rid of the front node. Alright, so 20 goes away. Well, makes sense. 20 goes away. So 10 is all that's left, right? One node. Right, so once again, we have two nodes. This one's pointing forward, this one's pointing backwards. I get rid of this one. This one was pointing backwards and away. The head, but we just removed it.
What'd you say? The 100.
Right, where it's it. Right.
I was gonna say, I
So in your top front, right? Look at your top front.
did like the first 5, and I've done like 1 or 2 after that.
So long as there's something there, right? We have a pointer to the head, right? We put head forward, right? So head is now the one, right? Right? If the head is null, right, then we do that. Otherwise, what?
Otherwise, that,
Then you can look at your computer or, it has just programs on it. Like, no, so there's programs on it.
okay,
If I bug you for a second, can I see your template.cpp and how you set up your templates? Because what I did is I followed the guidelines for the function, and I changed every part that I believe should be taken. And now I don't understand how the templates work. Do they go after the using statements?
It's always before it's everywhere. So before the declaration and before the definition. See, it's 22, right?
No, it's 21.
Oh,
Then I just start passing.
So we have to write the.
So yeah, the declarations have to have it.
Oh, that's what I'm missing.
Yeah.
Okay, yeah.
And then each.
Yeah. Wait, each definition has to have it too?
Yeah, where it's used. If it's not used, it doesn't need it, of course. But I think the objective.
I'll do that. That's probably what I'm missing because it's freaking out.
I'm not in this,
That one might have to say this.
yeah, I
And that's because we have to put them pop back because you say it then, right?
Right.
So here now, we're kind of that you keep back. I think we're listening. We call it Preorder, but we're listening to the resident. Oh. Good. Right, then I put 10 in the front, and put 5 in front of it. And then I put 20 in the back, and 25 in the back. So it should be, backwards should be 25, 20, 5. It says no. So. So 10 goes in the front, 5 goes in front of it, 20 goes at the end, and I go back. Which is why we get 5, 10, 20, 25. Right, but apparently when you push back on a list that has values, 25 at the tail end, it does not seem to be pointing backwards to 20. Right?
Oh.
But we get halfway, right? If 25 and it's not helping anything else, then for every reason when I go from 25 backwards, because this lag has all the backwards. And where you end up with problems in the lag is not going forwards, because you know
Yeah.
solve it backwards. It checks
Mutators don't, they just change the thing. Accessories.
That makes sense?
Right.
Right, and because I did push back and push front, and 25 went on the back, right? I'm gonna guess that's what.
Yeah. I just think of it like mutators obviously does that. Change mutation is changing something. And you also have need to return something.
So the head is going, the list is empty, a couple of stuff. It's not, right? So we're in this. So we create a new node, right? The old tail, right? We point forwards to the new tail. Does that make sense? And then you say the tail equals the new node. Okay, great. So the old tail is pointing forward to the new tail, and tail now points to the head. Right? When you create a node, any node, right? When you say new DL node, right? That automatically sets previous node and next node to what?
No.
Right. Here's your constructor. Here's your constructor. Right? When you construct a node, right? It sets previous node and next node to what? Does that make sense? So this new tail that got put in, right? The old tail is pointing forwards to the new tail. The new tail that was pointing backwards to where?
No.
Right, you never change that, right? And right default comes backwards to that. Right. So you can say tail set next to the new node, but then you have to say what?
Tail set previous to the.
Or what is tail? You don't change tail. All right, here.
Oh, set the new node previous?
Yeah, right. You
Yeah. The tail.
So the old tail was just still tail. You say set next to this new node, and now you say this new node set previous to the old tail. Now it's tails. And so now 25 should point to 20, right?
Right.
Now you're back in square root.
I believe all these.
For what, sorry?
Because, on the planes
Oh, yeah, that is case sensitive. That's you saying, yeah,
I just want, yeah, I guess I was doing that, I thought it was calling things. It's changing.
even your file names have to, yeah.
Oh, wow.
So, okay, so
Yeah, so like, assignment point, so you have the assignment point thing.
you say that.
Scroll all the way to the bottom.
Oh.
Those are what the problems have to be. They have to match that.
Yeah,
They should already, but yeah, you're good. Same as all of them.
Okay. Yeah. Oh, yeah, I'm like, there's so many S's. Is it, do I need to?
Yeah, but they don't always show up, but yeah. But like, Kevin's not here today, so we'll be.
Do I have to like email them saying like, you can do 2 weeks?
No, because I haven't created it yet.
Oh.
If you had a 0 or a no submission, then you would use.
Oh.
So you kind of get lucky. My lack of being on top of stuff benefited everyone. Right, and here you're changing root underscore. You have no root underscore in this function, so you don't want to deal with because the function is recursive. You don't want to then in your recursive function pull out something that's not being changed recursive. So you don't have to say root underscore equals insert because insert if the tree's null, insert is root. The ends by reference, right? So they are the same stuff. So you don't have to check root. It was just if insert is null, that's when you have context. Not necessarily. Just the first time, right? So insert says what? If the root is null, we add. Otherwise, if the value of the insert is smaller, we call the insert function again and we pass on the left child. Or if it's larger, we call insert and we pass on the right child. So we don't need a lot of stuff in the other, right? So this is right, so that would be insert. So you're saying if, right, insert's contents is smaller, so contents is greater, right, you're just going to call insert and then pass on contents and then insert the right. And pass on the right child on the right. Yeah, minus the all the equals then. It would actually be this one. Right? If where I'm at is not where I want to be, right? And the value is larger, right? The value is larger than where I'm currently at. So I'm going to insert it in the right place. Does that make sense? Yeah, no. Right? So then we go into this and then let that one take care of, right? Is it empty, is it not? Does that make sense? If the answer is no, meaning that there is no subtree, which could be the very beginning, right? The tree is totally empty, right? And so insert is null, is root, right? Or it could be that. So right now the root, right, is null for everything, right? If I want to add 5, then root and insert are the same thing. Insert's null, so I create a new node and I point insert to it, but because it's by reference, they're actually same. They're the same thing. Does that make sense? Yeah. Right? And when you create a node, this is null, right? So some value comes in. And then the next time, same thing happens. We come in, I want to add 8, right? Well, insert and root become the same thing. Insert's not null, right? 5 not less, but it is bigger, right? So I call the insert function again, and I pass in insert get right, which is this right arrow, which means in this instance, this is insert, right? And now insert is null, so now it applies the same algorithm. Well, it's null, add a child there, I update instead. We don't want to say something right now.
Very similar, but.
Yeah. But it's nice that it's replaced.
Does that have a double right idea?
That's what happens when I told you why I don't. So delete runs the.
I was just having delete what you call separately, I was going to keep that separately.
Yeah. Oh yeah. That is terrible.
Anyway, so yeah, this is before it gets called this.
There it is. It's going to have to be by reference when you start first.
The node.
Yeah, because you're going to have to update that. Go to 22.
Oh, what gets passed into it.
Yeah. So you have to like that. I mean, you can do this, but it's more than what you have to do. Because you can just go down, you're just protecting yourself from doing one more function call. You can just go one more function call down. So if you're here, right, you're here basically, and you're saying, well, if there's no more, right, there's nulls on both sides, then I can delete it. But really, you can just say, before I delete this, I want to go down the left tree. Oh, it's null, so I'm going to come back. Then we'll go down the right tree. Oh, it's null, then I come back, and I can delete it.
So how do you?
So you already have, because you have that check, right? Maybe you don't have that protection. So the first thing you would protect is not this. You would just say,